Hey there, welcome to Mechanical Engineering Explained. My name is Vishal and today I'm gonna show you how to solve a mechanical vibration problem by solving example. Generally I follow the mechanical vibration book by S.S. Rao, but you are free to follow any book. There might be some notation difference, but whole basic concept will be same. So let's get started with this example here. Engine of mass is 500 kg and mounted on an elastic foundation of equivalent stiffness 10 to 5 Newton per meter, and said determine the natural frequency of the system. So this is a simple example here, and just determine the natural frequency of system. So how we can solve first draw the mathematical modeling if you want. If you don't want to draw it for this example, it's fine, but generally I draw it so it's give a simple idea what I'm dealing with. K and M, and the mass here is a M 500 kg, and stiffness K here 7 into 10 raised to 5 Newton per meter, and says that determine the natural frequency of the system. It doesn't show find in a radian per second or in a hertz, so we find in both. Write down what is the natural frequency. As I saw in a theory, the natural frequency of the single degree of freedom undamped free vibration system, natural frequency will be omega n is equal to square root of k by m, and here we have both are known, k stiffness and mass, so we can directly find out the what's the natural frequency of the system. So 500 divided 7 into 10 raised to 5 divided by 500 square root, and it gives us 37.4 radian per second. This is the natural frequency of given system. If you want to find the natural frequency in hertz, so this is a angular natural frequency, and if you want to find the natural frequency in hertz, F is equal to omega n divided by 2 pi. So generally just divide this answer with the 2 pi, so it straightway gives a frequency in hertz is a 5.96 hertz. And if tell you that find the time period, so you can find the time period for given system from this equation. So is natural time period t is equal to 2 pi divided by omega n, generally like 1 divided by f, as also you can write down, and is 0.167 second. And if there is a initial condition for this system, is given like x0 and initial velocity, initial displacement, or initial velocity acceleration, then you can find out the response for the system, which can be the first we have to write out the equation of motion. So for given mathematical modeling, the equation motion will be mx double dot plus kx equal to 0, because there is a no damping, so it's a simple one. And the solution for this system is so there is a two possible solution. You can use any one, a1 cos omega nt plus a2 sin omega nt, or you can use a sin omega nt plus 5 bracket. And the solution of this equation gives you the displacement of the system, acceleration of the system, and velocity of the system. And here a is the amplitude of the system, and Once you put the initial condition, it gives you a displacement amplitude of the system by so you can use this equation directly, or you can just put the initial condition and then solve the equation, and goes to the x0 dot divided by omega n square. So x0 is the initial displacement and x dot 0 is the initial velocity and the natural frequency of the system. And the initial phase angle you can find by also the initial condition tan inverse omega n x0 divided by x dot 0. So this is the initial velocity, and this is x dot 0 is the initial displacement and natural frequency. So just on these three parameter you can find the amplitude of the system and the initial phase angle of the system. And also you can find the, when you solve the this solution by putting the initial condition, you can also determine the response of the system. That's all for today guys, and thank you.